To really get a good idea of what this theorem is saying, Stokes theorem, we kind of want to be able to plot this out and see exactly what's going on. So what I'm going to show now is for that half a torus surface, what Stokes theorem is actually saying. This is true for any surface that we're going to evaluate Stokes theorem on. So let's consider that surface that's like the half of a torus. From the previous problem, where we argued for how to correctly apply Stokes theorem to the cylindrical can, and if we run this code that I've written, you see a picture of, say, a sample vector field that's these black vectors, along with the unit normal vectors on the surface. So you can clearly see here the unit normal vectors at every single point on multiple different patches of the surface, along with some vector field f, which are the vectors that are pointing in different directions away from the normal vectors. Because this is a general vector field, we can interpret this as a curl vector field. So let's say this vector field f is the curl of some other vector field, and the idea is that we know that the amount of rotation at each individual point is going to be the normal to the curve is going to be the dot product of the normal vector at that point with the curl vector at that point. And that gives you the amount of infinitesimal rotation. So at all of these points, these base points, I've also plotted a colored point where the color corresponds to the value of this projection. The value of the dot product of the normal vector at that point with the curl vector at that point. So this corresponds to, say, this point right here is light blue, so this projection would be around a little bit over 0.5. And so on and so forth. You see that for each other individual vector that you can compute the projection. This one's red, so this is going to be in the negatives because the vector field, the curl vector field, and the normal vector at that point are not pointing along the same general direction. The idea is that we can do this at every single point. And what Stokes' theorem is saying is that if we find the accumulation of all of these projections, so the accumulation of the curl normal to this entire surface, it's exactly proportional to the circulation around the boundaries. This surface has two separate bounding curves, so we have to add both of those circulations in the direction that's consistent with the normal. So if we look at that, the boundaries, right, the circulation is going to be around in this direction right here and in this direction right here. So this is why we had to switch signs before. But perhaps a better visualization here is going to come if we, instead of plotting this shows exactly what we're computing, but the vectors here are getting a little bit unmanageable to look at. So if we increase the number of patches on our surface, this picture is going to become more and more clouded. So let's just kind of draw, using the tangent vectors, a box of rotation in each one of these boxes, each one of these patches. And I'll hide the vectors, and the vector field and the normal vectors. When we do that, this is what picture results. So we can see here, we have our surface, right, and in each one of these patches we have a rotation, and we're essentially measuring the amount of rotation the vector field is doing around each one of these points. The color of each dot here corresponds to the total amount of rotation in this individual direction. And this is exactly what the curl is measuring at each individual point. The curl here is a little bit different than the curl here, a little bit more than the curl here. So these curls don't entirely cancel out at the boundary. However, what Stokes' theorem is saying is that in the limit, as these patches become smaller and smaller and smaller, all of these intersections, or all of these, the boundaries between patches, the curl is canceling out at them, And what that means is that the total amount of accumulation of curl normal to the boundary in this surface, so in this region, is going to be directly directly equal to just the total amount of circulation on the boundary. And we can see this if we decrease the size of these patches. So as we decrease the size of the patches, they'll get smaller and smaller and smaller. However, we'll be able to see exactly what I'm talking about. So let's do this. In this picture, we have 10 patches plotted. Let's increase it to just 15 and see exactly what I'm talking about. So if we increase the number of patches to 15, you can see clearly that these patches are getting smaller and smaller and smaller on the boundary, and the values of curl in corresponding regions that are close to one another are getting closer and closer and closer together. And as long as the continuity assumptions on our function are satisfied, this is going to continue to happen. So we need those smoothness assumptions on the vector field in order for this to happen. But as long as we have those assumptions, right, as we increase the number of boxes here, and so these boxes are going to get smaller and smaller and smaller as we increase the total number, and the value of curl in each neighboring cells is going to end up canceling out, so that this cancellation effect all throughout, and you have to go all the way to the boundary to compute the total circulation. Let's jump up to 25. So with 25, you see even more. This is going from 15 to 25. You see even more of what I'm talking about, where the relative amount of circulation in each one of these small boxes, or the curl in each one of these small boxes, is essentially canceling out. So between these two boxes, the curl here is essentially the curl here. The circulation along these two edges cancels out, because each of these boxes we have to think of as rotating counterclockwise, and vice versa, all throughout this boundary right here, or all throughout this surface S. And it is getting a little bit, the picture even now is getting a little bit crowded, but you can see if you rotate it to a correct vantage point where you can see kind of the boundary, or even if you kind of rotate this around, see different parts of the boundary, you're seeing that very clearly. At each one of these boxes, the circulation is canceling out, because essentially it's becoming equal. And in the limit, as long as our differentiability requirements are satisfied, this is going to be the case. There's just one more plot here to show you that. Right? That surface integral of the curl, in the limit, these boxes are getting really, really small. But as long as they, the requirements of the theorem are satisfied, because of the fact that these boxes are getting smaller and smaller and smaller, you get a cancellation effect in between neighboring cells, because the circulation here going down is canceling the circulation going up on this boundary right here. So that gives you a propagation all the way to each one of these boundaries here. So next I want to get into some applications of Stokes' theorem. This is the next thing we'll talk about. And I'll say that the biggest application here that we have is that Stokes Theorem reduces certain classes, or a certain class, of surface integrals to line integrals. And vice versa. So very often we'll use this if we have a complicated surface integral that we have to compute. We can instead convert it to a line integral, or if on the other hand we have a very difficult line integral, sometimes the surface integral is easier to calculate by using Stokes' theorem. Perhaps more importantly, right, this characterizes the class of vector fields that have surface independent surface integrals. Resting on some curve or a collection of curves, or the base curve C. So mathematically, this is the big power here that we have, and this is what I'll talk about right now, and as well as giving you a little bit of a caution, because we have to be very careful with this idea, just like all of the other things that we've talked about. So we'll assume that F is a purely rotational vector field. And you'll recall that what this means is that there exists some vector potential such that F can be written as the curl of this vector potential A. And in order to apply Stokes' theorem in the proof, we're going to have to assume that A is C2, or twice continuously differentiable on our domain. So we can show that the surface integral over any surface S of F dot n hat, this is the closed surface integral over any closed surface, is equal to 0. For any piecewise smooth closed orientable surface S. And the question is, how can we do this? Well, for any closed orientable surface S, say S looks like this, we can always draw an oriented curve C going around the boundary of S, which splits it into two parts, S1 and S2. So S here is equal to the union of the surface S1 and S2. And if C is oriented as such, so going around our typical orientation, then we know from Stokes' theorem that the surface integral of f dot n hat ds over S1 is going to be equal to the line integral over C of A dot dr, the circulation of A around C. Because remember that from our assumption, F is equal to the curl of A, because it's purely rotational. Likewise, if we do the exact same thing for S2, we have that the surface integral over S2 of f dot n hat ds is going to be equal to the closed line integral, not over C, but over C traversing the opposite orientation. Because if we want to be, we have to be consistent with our normal vectors, and if our normal vectors on S1 are outward like this, with respect to the orientation of C, our normal vectors also have to be outward pointing on S2. Which is going to mean that in order to keep this consistency in our normal field, we're going to have to traverse C in the opposite orientation. And we know from our properties of line integrals that the line integral of C traversed in the opposite orientation is going to be negative times C traversed in the normal orientation. So this gives us a couple different facts here already. Right? What we're seeing is that the surface integral along S1, the open surface S1, of f dot n hat is going to be equal to negative surface integral over S2 of f dot n hat So the first thing this is telling us is that for a vector field that's purely rotational, the surface integrals themselves are surface independent, because S1 and S2 here are arbitrary. So as long as you can take two surfaces S1 and S2 and connected, they form a closed surface like this, the boundary curve C. We have that the integral of circulation of F on the top portion is always going to be equal to negative the integral of circulation of the bottom portion. Furthermore, if we rewrite this equation by adding this surface integral to both sides, we get that the surface integral over S1 union S2, which is a closed surface when I add put these together, of F dot n hat ds is going to be equal to 0, which shows exactly what we wanted to show. So this is very, very special and allows us to do some very similar things to what we did with conservative vector fields, but also for purely rotational vector fields, which is very, 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 very neat and very, very important. So this exercise shows us that what classifies as a surface-independent integral, or a certain class of surface-independent surface integrals, mainly the flux of a purely rotational vector field over a closed surface is 0. This is what we've shown. We can also use Stokes' theorem to establish some results on path independence that we're already a little bit familiar with. Namely, if D is a simply connected this is a very important assumption domain in R3 in three-dimensional space, and F is curl free, and continuously differentiable in D, then by Stokes' theorem, the line integral over any curve C of the vector field F, the circulation of F around any curve C, can be connected to surface integral over S of the curl of this vector field F. But because this vector field F is curl free, or is going to be irrotational, for any surface S, this is just going to be the surface integral of the constant function 0, because the curl is 0. So therefore, the closed contour integral over C is going to be 0, and the circulation of F is going to be 0 over any curve in this region, which is very, very cool and directly connected to some of the previous stuff that we've talked about, only it's a much more direct method of proving this result. Now, an important remark here, just like we've talked about before, the simple assumption of simple connectivity is very, very important. And I can't stress this enough. previous conclusion does not hold for domains which are not simply connected. And we've seen a number of different examples of this already. So what I actually want to do is bring in a very practical example, and that's the lift of that's created over an airplane wing or an airfoil. So we'll consider the following example. So we'll consider an airfoil of some shape. It's we'll represent it as going infinitely long in the y direction. There'll be x, z here, and then this is a snapshot in the xz plane of the shape of this airfoil. You can imagine this going all the way along the y-axis, infinitely far. So as the plane starts to increase its velocity, fluid is going to flow over the wing in a characteristic flow pattern where streamlines sort of look like this. So this is the streamlines of the velocity flow field as a function of position. And we know here that this domain, we're considering the fluid flow field around this domain right here. So our total domain in three-dimensional space is not simply connected, because we have this big kind of cutout of our domain corresponding to the airplane wing. Now, for such a flow, under certain assumptions, we have directly that the curl of this flow is going to be 0. So it's going to be irrotational under steady, nice flow conditions. However, if we take the line integral around any closed path C, so some closed path C that surrounds the airplane wing, just because the curl of this vector field is 0, we do not expect the circulation around C to be equal to 0. We've seen a couple different examples of this already in terms of just purely mathematical vector fields. This is a not equal sign. And then the main idea is that because our domain is not topological, not simple, so it's not a simply connected domain. And this is actually a really important point. It's actually very, very important for aerodynamics. It's very, very important because we have that the net lifting force applied to the airfoil we can show is proportional to this line integral. I'm not going to go into the derivation of this. It's a little bit long, but the main idea is that if we define rho infinity as the fluid density far upstream, and we define v infinity as the fluid velocity far upstream, and lastly, we'll define L prime as the force per unit length perpendicular to v infinity. What can be shown is that L prime is equal to rho infinity times v infinity times gamma, where gamma is that the line integral of the contour of v dot n hat, or v dot t hat along x, or along the curve C. So it's the circulation of the velocity, the fluid flow field. This is called the Kuda-Joukowski theorem. And it's very, very important in aerodynamics. And we can actually do similar things for electromagnetic applications as well, where you kind of look at what the power being produced around a solenoidal coil, and similar type problems. But it turns out that very often in applications we have domains which we're solving for some sort of vector field or field. When we have domains inside the region that we're solving for that are not simply connected. So we have to be very, very careful with applying these theorems. But they do have a lot of physical relevance. This is just one good example of that. And another application that we can do with the curl, with Stokes Theorem in particular, is to apply it to the curl. And this is going to actually explain what we talked about before. before. So if you remember, when we introduced the line integral, we actually redefined curl, came up with an alternative definition. That the curl of f normal to a vector n, or in the direction of a vector n, at some point r in our domain is going to be equal to the limit as delta A goes to 0 of the circulation around delta C divided by the size of delta A, the area of surface delta A. And we actually use this in a number of different homework problems to show that this is consistent. So the idea here is that as long as all of the theorems of so f is a nice enough, smooth enough function, so C1, we can directly apply Stokes theorem to this this equation up here, the circulation integral around delta C. And that's going to kind of prove why our two definitions of curl are consistent to one another. Let's go through and show this. So if we look at line integral over delta C of f dot dr, the circulation integral of f, as long as all of our considerations are satisfied for the vector field f in delta C and delta A, which all of them are, because delta A and delta C are getting very, very small around a given point. So you remember, if we have direction n hat, and we have some curve delta C that's traveling around this point n hat, and delta A is some surface that's created by filling in between this curve delta C. These things are getting very, very, very small. So the idea is that eventually we can get, at any point, we can get small enough so that the point-wise the conditions of Stokes theorems is satisfied. So this integral, the circulation integral, is the same thing as the double integral over delta A by Stokes theorem of the cross product of the curl, the del operator, with f dot or with n hat d s and this is probably the most important thing to do here. So we have what's called if you remember the mean value theorem for 1D, we can also apply the mean value theorem to multivariable integrals as well. So by the mean value theorem, there exists a point, we call it r star, in delta A, so on delta A, this bounding surface for each delta A, such that this double integral right here is going to be exactly equal to the integrand, which is the curl of f dotted with n hat evaluated at this point r star times delta A. And so now when we look at the limit as delta A goes to 0, of this ratio right here, we have this is going to be the same thing as the limit as delta A goes to 0 of the curl of f times the size of delta A divided by delta A, size of surface area of that surface. So the delta A is cancel out, and we're left with this is the limit of the curl of f dotted with n hat, where this is evaluated though at that r star, each one of which I guess we should, instead of calling this r star, we can probably call it, instead of r star, r delta A, because in general we have a different value of this for each value of delta A. I want to emphasize that we're applying the mean value theorem for every surface, as delta A shrinks. But the magic here now is that, r delta A is trapped inside delta A, and as delta A goes to 0, this is converging just to this point r right here, the center point of this evaluation. And so we've just shown that this limit is exactly equal to the curl of f dotted with n hat at the point r, which is exactly how we defined the curl initially, in terms of the partial derivatives and the cross product operation. So this is really nice. It's essentially, it's proven for us that the curl of a vector field can be definitively evaluated at a point using this operation. So it really does give you the local rotation of a vector field at a given point when you compute the curl of the vector field f. And not only that, but in some sense it gives you a measure of the potentiality of the field. We do have to be careful about whether or not the domain is simply connected or not, as we've seen. But this is a very, very nice result. So I'll consider one final example, which will be an explicit example. So let's consider the surface S. Defined by the graph z is equal to e to the negative x plus y squared. Over the circle d, the region D, which is the set of all points into D, such that x squared plus y squared is less than or equal to 1. So this is our surface, and we can consider the vector field F given by e to the y plus z minus 2y for the x component, the p function, x times y e to the y plus z plus y for our q function, and then lastly e to the x plus y for our function. Now, for this problem, no matter how you go through and try and do it, integrating over this surface is not going to give you a nice integral, regardless of whether you use the line integral, right, or for the circulation around the boundary of this surface, or whether you use the double surface integral, the surface integral over the surface itself. So you get kind of an idea of what this surface looks like. In 3D, you know that the boundary for the domain between of x and y is going to be a circle of radius 1. And the graph of this function is going to look like the function e to the negative r squared. When you plot out those functions, it's going to look kind of like a bump function that depends on the radius. Z equals e to the negative x squared plus y squared. So this is the surface that we're integrating over here. And you can go through like you normally would, calculate the curl. This would be good for you to check. But when I take the curl of this vector field right here, the curl is going to end up being e to the x plus y minus x times e to the y plus z. That's the first component of curl. The second component of curl will end up being e to the y plus z minus e to the x plus y. And the third component of curl is just going to be 2. This is going to hopefully give you a hint as to how we're going to go through and solve this problem. For we want to get the total accumulation of curl on this surface S. So in this problem, what we're looking for, right, to evaluate the accumulation of the curl of the vector field S normal to this surface S. And no matter which method you choose of going about doing this, you're going to get a not super nice integral. For instance, if we were to go through and just directly try to calculate the surface integral over this surface S of the curl of F, when all is said and done, this is going to become the double integral over d when we plug in of the function, the very long function. It'll be 2x of the curl of f dotted with n. So a first step to getting this expression would have to be, we evaluate the curl, and then we also evaluate the normal vector to the surface, which in terms of x and y, this is going to be exactly equal to Rx cross Ry, which is just going to be equal to 2x e to the negative x squared plus y squared for its x component. Its y component is going to be 2y times e to the negative x squared plus y squared. And its j component, or its k component, or its z component, is just going to be 1. And this is using a formula that we've talked about before for getting that normal vector. But the idea then is that when we go through and evaluate the surface integral, we end up getting that this is the same thing as the integral over d of the curl of f at our point r of xy, the point on our surface, dotted with Rx cross Ry dx dy, or dy dx. So when you go through and try and compute this, you end up getting that this is the double integral of 2x times e to the negative x squared plus y squared times e to the x plus y minus x times e to the y plus z like I said, this is a relatively long surface integral, because now it's going to be this plus 2y times e to the negative x squared plus y squared times e to the y plus z minus e to the x plus y, and then lastly plus 2 dy dx. So this is not a double integral that is going to be in any way friendly to go through and evaluate. So I don't recommend proceeding directly in going through and trying to evaluate this double integral, because it's relatively long and there's no nice simplifications for it. The exact same thing happens, by the way, if we try to go through and directly use Stokes Theorem here. Right, so from Stokes Theorem, this does satisfy all of the conditions of Stokes Theorem, this vector field in this surface S. So we could try saying that, well, this double integral, the accumulation over S, with the curl of F dotted with n hat ds, from Stokes Theorem is going to be equal to the closed contour integral over the boundary curve, in this case the boundary curve being this curve C right here. But even going through and trying to evaluate directly this closed contour integral is not going to give us something very nice. Specifically, we know that this bounding curve, so C, is parameterized by R of t is equal to cosine t for the x-coordinate in the curve, sine of t for the y-coordinate in the curve, and the constant value, the height, when x squared plus y squared equals 1, and when x squared plus y squared equals 1, z is going to be equal to e to the negative 1, so it should be 1 over e. That's the height on the boundary. This is for t from 0 to 2 pi. So then when we go through and evaluate this, this is going to become the circulation integral of this f dot dr is going to be equal to the integral from 0 to 2 pi of f of r of t, which is, or not the f of r t, the curl of f of r t. Not the curl, the vector field f itself. So this vector field evaluated at r of t dot product with r prime of t dt so when we plug into f, the vector field f, we get that f of r of t. So to plug all of this into the vector field f of r of t is going to be e to the sine t plus 1 over e, all minus 2 sine of t. The y component is going to be cosine of t times e to the sine of t plus 1 over e plus sine of t and the z component is going to be e to the cosine of t plus sine of t. So this is what the vector field f is restricted to the curve r of t. When we plug in r of t into f, which is our standard operating procedure for directly evaluating line integrals This is going to be dotted with r prime of t, which is going to be negative sine of t cosine of t 0. And taking this dot product then gives us that the integral that we have to evaluate for the circulation is the integral from 0 to 2 pi of negative sine of t times e to the sine of t plus 1 over e minus 2 sine of t plus cosine of t times cosine of t times e to the sine of t plus 1 over e plus sine of t. dt. Which again is way too complicated to go through and evaluate. It's not a nice integral even in 1D for the circulation. So the idea is that instead of dealing with these difficult integrals, so dealing with this integral right here or dealing with this integral right here, right, in both cases, even when we directly use Stokes Theorem, we get an integral that's not easy to evaluate or not nice to evaluate. But what saves us for this problem is the path independence talked about before. All right, we have that for this region. This is our curve C. This is our surface S. Right, we can take any other surface that we want, S prime, and we know that if the normals are oriented like this on S, and we reverse the orientation of the normals on S prime, right, so these the orientation of the normals on S prime is pointing in, the orientation of the normals on S is pointing out. We know that Stokes Theorem is going to give us the same result for integration along C, because the boundary of each one of these surfaces is the same. So the surface integral of the curl of F on S because this is the integration of the curl of this vector field F because of the surface independence property we talked about before. This is the same thing as the integral over S prime of the curl of F dotted with N prime ds for any surface S prime. And because I reversed the normals on S prime, the boundaries of these two expressions are the same as well. So the boundary of both these curves is C oriented normally, so oriented counterclockwise. Right, and both of these integrals are going to be equal to this. So what we're going to do to solve this problem in the easiest way possible is just choose the simplest possible S prime, which is just going to be the circle of radius 1 at z equals 1 over e. So S prime is going to be the set of points x, y, z in R3 such that x squared plus y squared is less than or equal to 1 and z is equal to 1 over e. And from our surface independence property, this integral, the integral that we're looking for, the double integral that we're looking for, in both of these values, by the way, so the integral of this double integral right here and this single integral right here, going to be equal to double integral over S prime of curl of f dotted with n prime, the normal to S prime, ds, and going through and evaluating this, well, n prime is constant. If we choose S prime to be this circle right here, the normal vector to n prime is exactly just the k hat. So this expression right here is going to be, when we evaluate it, double integral over d of this curl vector, the curl of f at points on this surface, dot product with the new normal vector, dot product with n prime, which is 0, 0, 1, is just k hat, which is extremely nice because now this becomes the double integral over d of 0 times this complicated function of x and y, 0 times this complicated function of x and y, and then 2 times 1. So our result is going to be 2 times double integral over d of 1 dy dx, which is just the area of our circle, or the area of S prime actually. It's the same as the area of S prime, just 2 times pi. So this is a really good example to show how to correctly use this idea of Stokes theorem, even in the case sometimes of having a very complicated double integral or a complicated single integral when you go through to do the line integral. But this will conclude today's lecture. Thank you very much for tuning in, and I hope you learned something and had a great day.